All right, so the first thing I'll mention is that I had said, make the homework due this evening, and that way you can come to my office hours today. No, you can't, because there's a faculty meeting that will take away my office hours. So, while you're certainly welcome to turn in homework tonight, you can also turn it in tomorrow instead, so that you can have quality time with me. Or you can already have turned it in, and then it's out of your hair, right? That's awesome, of course. But yeah, so that'll be the deal with that. Okay, we are going to launch ourselves into Chapter 9 today about stellar atmospheres, radiation transfer, and so forth. And so we're going to have some more fun. I think it's fun personally, with specific intensity, etc., etc. So we are, again, I'll emphasize now, we're in Chapter 9, stellar atmospheres. And we're going to do description of the radiation field, which is certainly important to understand when we're talking about transport of radiation through a stellar atmosphere, formation of spectral lines, and so forth. So it's time to have more fun with specific intensity. So first of all, remember that for the specific intensity, the flux per solid angle, essentially, that I lambda is the ratio of all these things as all these quantities become small and it approaches a limit, all that sort of thing. It's dE lambda over d lambda dt dA cos theta d omega. Remember, it's the ratio of all those things, and that's not a derivative, it's a limit as all those thingies approach zero. So I'm not bothering to write limit as that list of things goes to zero. I'm just saying there it is in all of its glory there. And remember that dE lambda is and it's a mouthful, energy emitted in the wavelength range from lambda to lambda plus d lambda, so in some narrow range of wavelengths, in time dt, in a little time interval dt, from area dA, if we're talking about emission from some surface, from area dA, at angle theta from the normal to the surface, into solid angle d omega. Right, so we had this idea of here's a little patch of surface dA, and here is the outward normal to the surface. We're talking about radiation going into some little solid angle cone d omega. There's d omega there, right? At angle theta to the normal. That's what the specific intensity represents in the end. So it differs from flux in that we worry about direction. Flux is when we integrate over solid angle and get the total amount of energy per second per square meter from our surface, our watts per square meter. But here we're worrying about the directionality. So watts per square meter per steradian and all those units. So we played a lot with it before. What do we call I lambda when it is a perfect thermal spectrum, a Planck spectrum? Then we give it the special symbol. What does that be? Oh man, I'm trying so hard here. For thermal radiation, yeah, what's the symbol be for I lambda when it's thermal radiation? I think you said it. B sub lambda. Oh, man. What is it B? And that's supposed to be like, oh, ha, 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 ha. I see what you're doing there, Dr. Harmon. No, it's B lambda, right? We call I lambda for thermal radiation B lambda, right? So that's the specific case. But radiation doesn't have to be thermal, so here's the general definition. It's all of those things for whatever our radiation looks like. If it's thermal radiation, perfect thermal radiation, then I lambda is B lambda, the Planck function, right? Which is that 2 pi HC, all that kind of stuff, e to the minus, all that business, over lambda to the fifth, anyway, the Planck function, okay? So I'll let people catch up in writing. What questions might you have at this point? Could this be more fun? The answer is no, it could not. This is good stuff. So let's have some more fun with it here. So the mean intensity, mean as an average, not mean as an intensity. It says, I hate everything, right? I hate you, I hate. Mean intensity, the average intensity, is, so remember we often use angle brackets to represent the average of a quantity. In quantum mechanics we call that an expectation value, but in general physicists like to use angle brackets like that to represent to represent the average of a quantity. Just as an aside, if you're using LaTeX, you can create that by putting whatever it is in between Langle and Wrangle. In other words, a left angle bracket and a right angle bracket. Don't use greater than and less than. That's not quite the same. And also these will automatically resize. So if you have a fraction in there, it'll make big ones and so forth. So Langle and Wrangle is how you get expectation value or means like that in LaTeX, which I kind of like. So this is defined to be the integral of I lambda over solid angles. So in every direction, divided by the integral of d omega over every direction. So that's, remember, in general, if we have an average of some quantity, the integral average is defined by integrate that quantity in one dimension, right? The average value of f of x is defined to be the integral over some interval a to b is defined to be the integral of f of x between a and b over the integral of dx between a and b, right? So in other words, it's equal to 1 over b minus a, integral from a to b of f of x dx. So the average of f of x is the constant value of f of x that would give the same value for the integral. And you should understand that that's where that definition is coming from. The average value of f of x is the thing when you multiply by b minus a that has the same area under the curve, right? So if this is f of x, there's b, the average value of f of x over the interval, so it'd be maybe somewhere like that, is the constant value that would have the same area under the curve as the actual function does, and that's why you call it the average value. And here we're doing something similar. In other words, the average value of I lambda is the constant that would give the same value of integrating the actual I lambda as a function of direction over solid angle. So that's why it has that definition. It's the constant value of the specific intensity. It would have the same integral over solid angle as the actual specific intensity function does. So I'll put that out here. I lambda is the constant value, mean of I lambda, I should say, is the constant value for I lambda that would yield the same integral over solid angle as the actual I lambda does. And I'm going to write it as a function of spherical coordinates. I don't have to, but I lambda can depend on direction. And so if we use a spherical coordinate system, then it would be I lambda as a function of theta. But what dat? What's that denominator? If I integrate over solid angle, all directions, what's that equal to? In other words, how many steradians are in a sphere, so to speak, right? Because when we talk about solid angle, if we integrate over solid angle, if we add up every possible solid angle, so to speak, if we make our solid angle cone, if we make it span all possible directions, we get the number of steradians in a sphere, which is what? 4 pi. 4 pi. Yep. You want that to be just totally memorized, just like you know how many radians are in a circle. 2 pi, steradians in a sphere, 4 pi when we go to solid angle. So that numerator is just 4 pi. So in other words, we can also say that this is 1 over 4 pi times the integral of I lambda over solid angle. And to actually do the integral, we want to have a coordinate system we've set up. A spherical coordinate system is a great choice here. So anybody remember what in spherical coordinates, what's our expression for d omega? What's d omega in spherical coordinates? So you're on the right track, and that so if I have a little area patch on a sphere that defines my solid angle cone, it slices that little area off the sphere, then remember, yes, that d omega is dA over r squared, where r is the radius of the sphere. And in spherical coordinates, what's our expression for dA in terms of r and theta and phi?
Sine.
Yeah, you're on, yeah, basically, right? Yes. It works out to be sine theta, d theta, d phi in spherical coordinates, because dA is r squared sine theta, d theta, d phi. If I make a little spherical rectangle spanning d phi in azimuth and d theta in colatitude, if you will, so then d omega is dA over r squared, and so that'll be just sine theta, d theta, d phi, and I feel like I should put the picture up because I want to be sure that you understand this before we go further. So I'm going to take a moment to fire up the projector and my laptop and all that good stuff. And this is another one of those things. You do want to just be so familiar with this that it's just almost knee-jerk reaction for you to recall this, because this doesn't show up just here. It shows up everywhere. It shows up in E&M. It shows up in quantum mechanics and so on and so forth. It's everywhere. Hi. Okay. Get myself logged in here. Get the projector fired up. Get the screen coming down. Get myself tripping on the cord. Get myself ready to make the screen stop going too far. No, what are you doing? Stop it. Okay. Right, so you've seen this before. This will be a reminder, I'm hoping. Wake up. See it. This business. That right there. Right, because if we imagine we got a little spherical rectangular patch there. You want to remember that if you want to define the area of that rectangle, here we're doing it like it's a unit sphere, like r is 1. In general, if r is not 1, then this distance right here is r d theta. Right, makes sense? Because r d theta will be that little arc right there, r d theta. And then this distance, well, this distance right here is r sine theta, because we got a right triangle. It doesn't look like it in this perspective drawing, but this is a right angle right here. And so we've got that this little arc right here is of radius r sine theta, because it's around the z-axis that it's pivoting, not around the origin, unlike d theta. So this distance right here is r sine theta. And so we turn through an angle d phi as part of a circle of radius r sine theta. So this distance is r sine theta d phi. So the whole area of the rectangular patch is r sine theta d phi times r d theta, or in other words, r squared sine theta d phi. So the solid angle that the patch subtends at the origin is dA over r squared sine theta d phi, over r squared, just plain sine theta d phi. So burn that into your brain, that d omega in spherical coordinates, where we define the z-axis as, or the x and y axes as in the plane of dA, and the z-axis perpendicular to that, d omega is sine theta d phi. Because boy, are we ever going to use that a lot. All right, makes sense? What questions do you have? Burn that into your brain. You are like, you can just reconstruct that diagram in a heartbeat, because you should be able to do that. That should be very easy for you to reconstruct for yourself. So, what questions do you have versus also, could you say that again? Right? You look like you have a could you say that again maybe, or?
Oh, no, I'm just So that's explaining it not in terms of the radius at all.
Because, yeah, see, because remember that the solid angle isn't going to depend on the radius of the sphere.
It's going to be the same angle.
It's going to be the, right. So if I made the sphere bigger, the area would get bigger at the same rate that the area of the whole sphere is getting bigger, right? Yeah, so it's going to be just proportional, right? The r squareds cancel, right? Whatever the radius of the sphere is, r squared sine theta d phi is the area of the patch. But then when I divide by r squared to get the solid angle, the r squareds cancel. Because the solid angle is a property of just that cone itself, not what particular sphere you cut off with. So yeah, so d omega is sine theta d phi. There ain't no r there. It's just sine theta d phi. Yep. Okay. Anything else? Yes.
So they do this for this sort of forming like a square. So like the thing you're talking about where it's almost like a silhouette of like an image, and it can be some like arbitrary shape. How does that?
Well, yeah. So that would be the situation, right? You take Calc 3, and you want to do area integrals, right? And so if the shape of the area that you're trying to find is nice enough, then you might actually be able to carry out the integration. But in general, if you just have some weird shaped area on the surface of a sphere, then you just kind of write that, well, if I integrate r squared sine theta d phi over that little area, I will get its area, but it might be hard to do in practice. It might be virtually impossible to do it in practice, right? Most area integrals for some arbitrary shape of the area, you can't actually do them, but you can write out in principle that integrate dx dy over this area and you get the right. And this is the same thing here. In other words, we can always say that the total solid angle for something is the integral of sine theta d phi over the range of thetas and phis that are fully defining it. If it's a really weird shaped cone, you might not actually be able to do the integral in practice other than with numerical approximation. But under the right circumstances where it's simple enough, then you can actually do the integral.
Okay.
Yeah, that's the sort of thing we're doing here. And we're going to give ones where we can actually do the integral. Yeah. So in particular, here, well, we're integrating over all solid angle. I didn't put any limits on here, and when I don't, it kind of indicates you're doing it over all solid angle. Whereas if I'm only doing it over some range of it, then I would start making specific designations there. So this is overall solid angle. So let's be specific here about the mean specific intensity. So that means we're going to do 1 over 4 pi. So if we actually carry out this integration over all directions, well, that says, okay, we let theta, which way do I want to do it? We'll let phi go from what to what? We'll let theta go from what to what of I lambda as a function of theta and phi, right? In other words, given theta and phi, the direction we're talking about, we would know what presumably I lambda is in that particular direction. I lambda theta and phi d omega is sine theta d phi. If I'm integrating over all directions, phi goes from what to what?
0 to 5 0.
No, because remember, phi is the azimuthal angle. So one thing you have to get out of your head is mathematicians reverse the definitions of theta and phi. For us, phi is the azimuthal angle, right? So if I swing over all possible values of phi, I went all the way around. 2 pi, yeah. So phi goes from 0 to 2 pi. And if I do every possible theta, I go from straight up, which is theta equals what? 0, to straight down, which is theta equals what? Pi. So theta goes from 0 to pi. Now Whether or not you can actually do the integral is going to depend on what I of theta and phi is, right? Just like anything else. Some integrals you can do, some you can't. So here's the generic expression, which you may or may not be able to actually carry out the integral, depending on what I lambda as a function of theta and phi is. But if I lambda is isotropic, what does isotropic mean? Same in all directions, right? Same in all directions. Then it can come out of the integral. And in that case, the mean value of I lambda is I lambda over 4 pi times the integral over solid angle. So if I wanted, I could say it's the integral from phi equals 0 to 2 pi, integral from theta equals 0 to pi of sine theta d phi, but that's going to give me the integral over solid angle. And what is the integral over all solid angle? 4 pi. So in other words, if the radiation is isotropic, the mean intensity is the intensity. But that makes sense, right? The average of something that is constant is the something, right? So for isotropic radiation, whatever I lambda is, that's also the mean intensity. All that's saying is I'm averaging a constant. And when you average a constant, you get the constant, right? The average value of 7 is 7. The average value of 6 is 6, and so on and so forth. If I have 1 million people and they're all 20 years old, what's their average age? 20, right? So that's the idea that this is saying there. So in that case, why, sure. Why blackbody radiation is isotropic. It's the same in all directions. So for blackbody radiation, the mean intensity is just B lambda, because I lambda is B lambda. So we've been talking about specific intensity, we've been talking about flux. Another interesting quantity for a radiation field is what is the energy per unit volume? How much energy in the form of photons is there for every unit volume, right? A local radiation energy density. Now we want the energy density which we're going to call U lambda. It's just a common name for it. What will its units be? The energy density, the energy per unit volume. So for an SI, what are its units? What's the SI? Yeah.
Joules per meter.
Yeah, joules per cubic meter, right? So this will be joules per cubic meter. Want to see a derivation? Read the book or my notes based on it. It's pretty cool, but it's a little lengthy, and so I don't want to spend class time on it. So it's not terribly hard, it's just a little lengthy, and I don't want to devote class time to this derivation. It's a clever derivation, I really like it, but still. We're just going to quote the final result here, and it is that U lambda is equal to 4 pi over c times the mean intensity. Turns out that if you know the mean intensity, multiply that by 4 pi over c, and you got yourself the energy per unit volume in the radiation field. That's a really important expression, so let's put a box around it. And so again, if you've got an isotropic radiation field, then whatever the intensity is, that's certainly also the average value of the intensity. And so in that case, U lambda is just 4 pi over c I lambda, whatever I lambda happens to be. And so for thermal radiation, let's see, for thermal radiation, what's the mean intensity equal to? B lambda, right? Because I lambda by definition is B lambda for thermal. B lambda is I lambda for thermal radiation, that's its definition. And it's isotropic, so in particular we can say for pure thermal radiation, blackbody radiation, U lambda is 4 pi over c B lambda, but we have an expression for B lambda, and so let's go ahead and multiply it by 4 pi over c, and that gives us 8 pi h c over lambda to the 5th power divided by that magic denominator, e to the hc over lambda kt minus 1. Just putting in what B lambda is and multiplying by 4 pi over c. That's the energy density in thermal radiation. And you'll have fun for the homework that's due at the end of the week doing things like, okay, I can write an expression for how much energy is in an oven at a given temperature, and I can say, okay, well, how many photons are in there, and stuff like that, cute things like that. For that, we need to go from U lambda to U, in other words, integrate overall wavelengths. What is the total energy density, as opposed to U lambda is the wavelength-specific energy density, where U lambda d lambda would be energy per cubic meter. Right, so note U lambda d lambda equals joules per cubic meter in wavelength range from lambda to lambda plus d lambda. So according to the formula, how much energy is there at any specific wavelength? You can ponder that while you're copying that. So how much energy is there per cubic meter at a wavelength of exactly 500 nanometers for a temperature of 5,000 Kelvin, let's say? And the reason I'm feeling so free to specify that and ask you to give me the number is it doesn't require any calculation whatsoever. I'm seeing the magic symbol. Yes, the answer is 0 according to the formula. There's no energy at any specific wavelength. And we met something similar when we talked about the flux, how many watts per square meter coming out of the surface at any specific wavelength. If I'm looking at a range from lambda to lambda plus d lambda, and I say I want exactly one particular wavelength, exactly 500 nanometers, what's the width of the range of wavelengths between 500 nanometers and 500 nanometers? 0, right? D lambda is 0 for any specific wavelength. So the formula is saying there's no energy at any specific wavelength per cubic meter. You can only talk about energy for a little unit, for a little wavelength interval, right? And it's just one of those funny calculus kinds of things. We're treating the wavelengths as being continuous, and the photons might have, really specific wavelengths or whatever, but the probability of, if you had a wavelength of a photon of some perfect wavelength, strictly speaking, the probability of generating it is 0. You've really hit the jackpot for that particular wavelength. You've made something happen that really had a probability of 0, strictly speaking. Complications are that really photons don't have perfectly defined wavelengths, because to have a perfectly defined wavelength, something has to have existed forever in the past and the future and filled the entire universe out to infinity in all directions. That's hard to achieve. But just be aware of that subtlety, right? That we really can only talk about from our mathematics here, energy per cubic meter, or joules per cubic meter, in a range of wavelengths, not in any specific wavelength. So if I wanted to know how much energy there was between 500 nanometers and 700 nanometers, what would I do? What would I do with U lambda to get in between, say, lambda sub A and lambda sub B? How much energy per cubic meter is there between lambda sub A and lambda sub B? What would you do?
Integrate it over the range.
Yeah, right. So U between lambda sub A and lambda sub B. How much energy is there at wavelengths between lambda sub A and lambda sub B? Well, that would be the integral from lambda sub A to lambda sub B of U lambda d lambda. And remember too, again, I didn't mention it, but I'm hoping you would recognize U sub lambda is just funny notation. It's really U as a function of lambda, but instead of writing U parentheses lambda, we write it U sub lambda, just like we did F sub lambda for fluxes and B sub lambda for the black body radiation. It's just a notation we use for, as a function of lambda, we make a subscript. So the total energy in EM radiation, total energy, I should say density, because it's per volume, total energy density in EM radiation is going to be U equals, if I want all of it, what's my range of wavelengths? If I want all the radiation, what's the shortest possible wavelength? 0. What's the longest possible wavelength? Infinity. So I'd integrate from 0 to infinity. 0 to infinity of U sub lambda d lambda. Just integrate over all wavelengths to get the wavelength integrated energy density, the total energy density in all forms of electromagnetic radiation, wavelengths of electromagnetic radiation. Two, 4, 6, 8. Now it's time to integrate. Well, again, depending on what U lambda is, you may or may not actually be able to do the integral. But we can do the integral for thermal radiation. For thermal radiation, for blackbody radiation, this says U is 4 pi over c times the integral from 0 to infinity of b sub lambda d lambda So if we integrate f lambda d lambda over all wavelengths for thermal radiation, what did that give us? The integrated flux over all wavelengths for thermal radiation was what? So again, thermal radiation, if we let f lambda be the Planck function for flux, as opposed to specific intensity, what do you get for that? It's one of the radiation laws. I want the total flux, how many watts coming out of each square meter for thermal radiation. Why, there ought to be a law. Yes? There's no pi in this one because I'm doing f lambda. So I want the flux. Yeah. F is that integral, right, which you can do, right, which you did in homework, I do believe, and you get sigma t to the 4th power, right? You did a homework where you got a bunch of constants times t to the 4th power, so that bunch of constants must be what gets lumped together to be called sigma, the Stefan-Boltzmann constant. So we know that F is sigma t to the 4th power. We also know that f lambda is pi b lambda from before. That's also something we showed, that f lambda for thermal radiation is pi times b lambda. Right? This is the watts per square meter version. This is the watts per square meter per steradian version. And then when you integrate that over the outward hemisphere, you get pi. So we know that the integral of b lambda d lambda is the integral of f lambda d lambda over pi. So this integral right here is sigma t to the 4th power divided by pi. Or in other words, and this is a very important result, we get a version of the Stefan-Boltzmann law that instead of applying to flux, applies to energy density, energy per cubic meter. We get that for blackbody radiation, right, for BB radiation, for thermal radiation, this isn't a general result. For thermal radiation, U is equal to 4 sigma over c t to the 4th power. So just like the flux depends on temperature to the 4th power, the energy density also depends on temperature to the 4th power. Oh my God, when it was flux, we just had a single constant that we said times t to the 4th power gives the flux. Who wants to remember 3 things? 4 sigma over c? Nobody wants to do that. Let's just lump them together and call it A. So it's A t to the 4th power. Where A, just by definition, is 4 sigma over c. And if you run the numbers, that's 7.566 times 10 to the minus 14th power joules per cubic meter per Kelvin to the 4th power is the radiation constant. What an inspired name that is. They must have had a committee that spent a month trying to come up with that name for that. That's the radiation constant. Oh, sorry, 10 to the minus 16th power. 10 to the minus 16th power. Of course, that's a very small number, but it's t to the 4th power, right? If you put in 10,000 Kelvin, 10,000 to the 4th power is 10 to the 16 Kelvin to the 4th power. So now we're talking, you're getting like, you know, roughly at 10,000 Kelvin, about 7.5 joules per cubic meter are going to be in the radiation field at that point. Okay. What questions do you have? So you tell me the temperature, and I'll multiply it, I'll raise it to the 4th power, multiply by A, and that's how many joules per cubic meter are in the radiation field. If you want to know how many photons are in there, well, if you knew how much energy each photon had, ... for when you're doing the homework problem later. If I know how many total joules are in there, and I know how many joules each photon has, you can figure out how many total photons are in there, that sort of thing. And the answer will be a lot are in the oven. If I recall, it's on the order of like 10 to the 15th power. It's like a quadrillion or something like that. Or it would be in a typical like kitchen oven of photons of that thermal radiation. So we've met this beast before, and in fact we were just referring to what it gives for blackbody radiation. The radiative flux, well actually no, this isn't quite that. This is the radiative flux over all directions as opposed to over the outward hemisphere. So the radiative flux is the net energy per unit wavelength interval passing per second. So if I wanted to be more generic, I could say passing in a unit time interval, but I'll just say per second. And here I could be Mr. SI here and say, is the net number of joules, if I wanted. But for some reason, we tend to say energy per second per square meter instead of joules per second per square meter. You know, really consistent would be energy per unit area per unit time, or joules per square meter per second, right? Something like that. But we're not consistent. We'll say energy per second per square meter. So then you're like being specific about the energy. Not specific about the energy, but being specific about the time and the area. Who knows why we do that? But so I'm doing that too. Energy per unit wavelength interval passing per second per square meter if we're in SI, it'd be square centimeters. If we were in CGS, in the quote-unquote outward direction. So really, you imagine making a little surface, and you pick one direction to be outward and the other direction to be inward. And in E&M, you've done the same sorts of things, right? If you have an open surface, it's up to you which direction is out and which direction is in. If you have a closed surface, then out and in no longer are up to you. There's a definite outward and inward. But for an open surface, you have to pick. So if I have just some open surface, I pick which side I want to be the outward direction. For a star, it's pretty obvious which way to pick. It's the direction away from the center of the star. That's why I put it in quotes, though, because for an open surface, you would have to decide which direction is outward, in your opinion. I still have a moment. That's still a little quick there. So Yeah, okay, we'll just take the break now, and then we'll continue. Okay, let's continue our glorious ascent. I'm going to replace a gerund with a simple imperative. Let radiative flux, blah, blah, blah. So we're going to say, let the polar axis of a spherical coordinate system be normal to the surface element in the outward direction. Right, remember, the polar is the one we call z. The polar z-axis that's really the Cartesian axis, but in other words, when we think in terms of Cartesian transforming to spherical polar coordinates, we put z in that outward direction like that. But the polar axis of a spherical coordinate system be normal to the surface in the outward direction. Normal again means perpendicular. Normal to the surface in the outward direction. So here's our little surface. Here is that z-axis that we're talking about. And so the surface itself in Cartesian coordinates, those would be the xy axes, but then we define the spherical coordinates in the usual way, right? Phi is angle away from the x-axis, counterclockwise, looking down on the surface, blah, 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 blah. I'll put in parentheses here, the surface need not be a physical surface, right? We've just got photons everywhere, and I can just say, here's some mathematical surface, and I'm going to try to find the net flux through that mathematical surface. So the surface need not be a physical surface. It could just be some imaginary mathematical surface. So then what's our radiative flux? How would we find that? How would we find that radiative flux through that surface that we're interested in? So that would be F lambda is equal to, so what we would do is take dE lambda, d lambda, dt, dA, d omega. So in other words, energy per second per square meter per wavelength interval, and now it's per solid angle, but now I want to also integrate over solid angle. In other words, I'm going to find energy per second per square meter per wavelength interval into d omega for every possible direction, added up for d omegas in every possible direction. So I'm going to carry out that integral right there over all directions. I'll make that explicit by saying down here, over all directions. Or in other words, I would let theta go, I would let phi go from 0 to 2 pi, theta go from 0 to pi when I actually carry out the integration. But first, what is, can anybody blow my mind and impress me by saying, what is that stuff all in the parentheses there? It's not quite the specific intensity, although it's very similar, but what is it missing in the usual definition of the specific intensity? What's not in that definition? The cosine theta term. So all that stuff is I lambda cosine theta, because we didn't include the cosine theta term in it. So that's all I lambda cosine theta, because if I take I lambda cosine theta, that'll cancel out that cosine theta. It was down there in the denominator. So in other words, the radiative flux is the integral of I lambda cos theta d omega, whereas remember for the mean intensity it was just I lambda d omega. For the radiative flux we've got I lambda cos theta d omega that is showing up. And in terms of the spherical coordinate system we've set up, that's going to be I lambda cos theta times, what's d omega again? In spherical coordinates, d omega is right, sine theta d phi, yes. So it's going to be I lambda cos theta times sine theta d phi, and this is an integral over all directions, so it's going to be phi equals, theta equals, phi equals what to what? 0 to 2 pi. Theta equals 0 to pi. 0 to pi. So that's our beast. And again, I lambda is going to be a function in general of theta and phi, and whether we can actually explicitly do the integral is going to depend on what I lambda actually looks like. Only in the simplest cases would we be able to do the integral, but sometimes the cases are not too complicated. You can always numerically integrate, but like, you know, as you well know from calculus, there's plenty of integrals that you can write down that you can't actually do because they're just too hard to do, right? That's not hard to come up with at all, in ones where you couldn't do it. But we'll consider, okay, sometimes cases where I lambda is relatively simple, but we're going to make now a very, very standard transformation here. And if you've done anything resembling a senior project, a summer project with me, you would have seen this idea that we're going to define mu equals cosine theta. And I believe we did this before too earlier at one point. It is convenient to define, and you'll see that it's not just here that we'll want to make this definition. It is convenient to define mu equals cos theta. In other words, we're going to do an integration by substitution action here. What's d mu? If mu is cosine theta, then what's d mu? Yeah, cos differentiates to minus sine theta d theta, right? So d mu is minus sine theta d theta. And then when you do a definite integral by changing variables, you also have to change the limits. So in other words, we're changing the theta integral into a mu integration. So we have to figure out what's mu for theta equals 0, what's mu for theta equals pi. So we have mu of theta equals 0 is what? 1, right? Because it's cosine theta, so cosine of 0 is cosine of 0 equals 1. And mu of theta equals pi is cosine of pi, which is what? What's cosine of pi?
0.
No, that's pi over 2. Keep going. Minus 1, right? Minus 1, right? You've gone half a wavelength when you go to pi, right? The way I remember those things is I make the plot in my head, right? Or I draw the plot, right? Here's the plot of cos theta, right? There's 0, there's pi over 2, there's pi, right? So 1 there, minus 1 there. That's how I remember those things. I just think of what the plot looks like. Cosine of pi, which is minus 1. It is often the case that mu will be interested in radiation fields where mu doesn't depend on phi. In other words, where mu only depends on how far you are from the outward direction in angle and not where you are in azimuth. That's a very common, interesting case. So if I lambda does not depend on phi, which it often won't, like at the surface of a star. Typically, the radiation doesn't care about the azimuthal angle. It just cares how far you are away from the outward normals of the surface, not on the azimuthal angle, not on spinning around the normal direction to the surface. So if I lambda does not depend on phi, we can first do the phi integral, and maybe you already see what it'll do, but in other words, what this allows us to do is say, okay, well this will be the integral from phi equals 0 to 2 pi of just d phi by itself, because remember with multiple integrals, if your function doesn't depend on one of the variables, then you can just do that integration separately. So it'll be the integral on d phi times the integral from theta equals, so times the integral from mu equals 1 to minus 1 of I lambda, and then notice sine theta d theta is minus d mu, so this would be I lambda times minus d mu. So I've also done the integration by substitution for mu there. Does that make sense? Anybody not happy with that? What's that integral? If I integrate d phi from 0 to 2 pi, that's just 2 pi. So we get 2 pi, ew, a minus sign. What do I do to get rid of that? I could, but there's a better thing to do. Yeah, I want to flip the limits, right? You can flip the limits is what I really want to do. So this will be 2 pi integral from minus 1 to 1 of I lambda as a function of mu d mu. So in that very common case of azimuthal symmetry of the radiation field, it doesn't care about phi. F lambda is just 2 pi times the integral from minus 1 to 1 of I lambda d mu. Mu d mu, I meant to say. Mu d mu, right? Because, what did I do here? Yeah, so sine theta d phi, cos theta sine theta d theta d phi is minus mu d mu. I messed up. Nobody stopped me. Nobody stopped me. So this should have been I lambda times minus mu d mu in there. So there should be I lambda mu d mu for that integral right there. Because the whole point of doing the integration by substitution is to recognize the rest of it, right? So cos theta sine theta d theta without the phi, cos theta sine theta d theta, right, is minus mu d mu. Does that make sense? Okay. So there's I lambda as a function of mu. Sometimes we just drop that and say I lambda mu d mu. So for an isotropic radiation field, we'll get F lambda is equal to 2 pi I lambda times the integral from -1 to 1 of mu d mu. What's that going to give? Well, if I want to just be explicit, I've got 2 pi I lambda, and then what's the integral of mu? Oh, no, I just want mu itself because I'm doing the integral as mu. I've made a substitution, so I'm just treating mu as its own thingy. Yeah, mu, half mu squared, right? Mu integrates to half mu squared. So this is mu squared over 2 evaluated between -1 and +1. Which is what? What's half mu squared evaluated between -1 and +1? Well, that'll be 1 squared over 2 minus -1, the quantity squared over 2. Quick, what's that equal to?
0.
That's 0, right? The integral is 0. For an isotropic radiation field, the radiative flux is 0. Why does that make sense? Remember that the radiative flux is the net joules per square meter per second per wavelength interval flowing through your surface. If the radiation is isotropic, compare the amount of energy flowing outwards through the surface to the amount of energy flowing inwards through the surface, because the photons are moving in every direction. So I got my surface, there's radiation flowing outwards, there's radiation flowing inwards. If the radiation field is isotropic, how should those two things compare? They're equal to one another. There's just as much energy flowing out of the surface as flowing into the surface. So we want to note that this makes sense. Makes sense. Just as much energy is flowing inwards as flowing outwards. There's just as much energy flowing inwards as flowing outwards in any given second, in any given blah, 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 all that stuff, right? So it's all in balance there. So thermal radiation is isotropic. If the entire sun was all at the same temperature, how much energy would be transported out of any given spherical shell inside the sun? If it was all the same temperature, well, that would mean we had just this thermal radiation all specified by the same temperature. If it was all the same temperature, would the radiation be isotropic within it everywhere? If it's all the same temperature, it would be black body radiation everywhere, at least, you know, ideally, black body radiation everywhere, and so it would be an isotropic radiation field. So if you're at any place within the sun, compare how much energy is flowing outwards with how much energy is flowing inwards. They're equal. They're equal. An isotropic radiation field, there's no net transport of energy. There's just as much energy flowing out of any surface as flowing into any surface. So could the sun be all at the same temperature? Well, is the sun generating energy anywhere? Yes. Where? In its core. How's it doing it? It's fusing, nuclear fusion of hydrogen and helium. We haven't gotten to that yet, but you know that presumably the sun is fusing hydrogen and helium in its core. So it's generating energy in the core, and it's radiating energy from the surface. For there to be any hope of equilibrium, or at least a good quasi-static situation, just as much energy has to be coming out of the surface every second as is being dumped out of the core every second. But if the sun were all the same temperature, there would be no net outward transport of energy from the core towards the surface, and that would not work. So in other words, the temperature has to increase inwards in the sun so that there is a net outward flow of radiation, so that the radiation is brighter moving outwards than moving inwards. If you were inside the sun, it would be blindingly bright in every direction as you vaporized in short order. But if you could avoid that sad fate, you're in the sun, inside the sun, impervious to being vaporized by temperatures of 1,000,000 Kelvin or more, whatever. Well, and your eyes could, see really bright things and not just get saturated into ow. If you look towards the core, the radiation would be brighter than if you look towards the surface, because it's hotter towards the core, cooler towards the surface, so there would be a net transport of energy outwards. Yes?
If you did have a star that was all the same temperature, there just wouldn't be energy transfer?
Correct, yeah.
How would that affect like a plant nearby? Like would they feel heat?
So
Like a temperature?
So the thing is, right, so first of all, it's always going to be true that the surface temperature is lower than the core temperature, right? And so this couldn't happen. But suppose you could make it happen, right, just hypothetically. And you can get close to this in the core of a star that isn't generating nuclear energy, because in that case, it doesn't have to transport energy outwards. In fact, it better not, because if you're not generating any energy in the core, there shouldn't be any energy transported outwards. So the core can be essentially isothermal in that case, same temperature everywhere, because you don't need to transport energy outwards from it. But let's hypothetical star where it's all the same temperature everywhere. At the surface, what's the direction outwards? If you're right at the surface, if you look up, what do you see? Outer space, right? Is that as hot as the star is? No. So at the very surface, outer space, ow, ow, ow! So there will be transporting energy out of the surface anyway, right? So the thing would have to be slowly cooling at the very least, right? Because it's losing thermal energy. But this is within the star. We're below the surface here. There won't be any net transport outwards in that case. But still at the surface, space, ow, ow, ow! And so there is energy transported.
Like a planet nearby, so it's still experience like a little bit of heat, just wouldn't be as much as...
Yeah, or in fact, for a white dwarf, it's very small, but it's super hot. So if it had a cute little planet nearby, it'd be toasting. Yeah. Depends on how hot that surface is. Yeah. Yep, good question. What other questions? Okay, so this is the net flux. We can also talk about just the outward flux. And again, if we're talking about a star, there's a natural outward versus inward direction. If you have just a radiation field somewhere and you're just arbitrarily curious about it, you can put the surface any which way you want to. But for stars, keep in mind, outwards generally is going to mean the direction away from the center of the star. And so we might very well want to talk about the outward flux. The outward flux is, I only look at the outward hemisphere, so to speak. I'm only integrating over directions outwards. So F lambda out would be the integral over the quote-unquote outward hemisphere of I lambda cos theta d omega. So using our result there, that'll be 2 pi times the integral of I lambda mu d mu, but we have to decide our range of mu in this case. So we are going from theta equals 0 to pi, right? Not from theta equals 0 to pi. Now we're going from theta equals 0 to, I only want the outward directions. So here's theta equals 0 to, what's our final value of theta? Theta equals 0 to, I only want outward direction. Here's the table, right? If I only want outward directions, here's theta equals 0. I don't go all the way to pi, to theta equals pi. I only go down that far. What angle is that? Pi over 2. So our theta angle only goes to pi over 2, and mu of pi over 2, cosine of pi over 2 is what? 0, 0, 0. So in this case, the mu integral only goes from 0 to 1 instead of from minus 1 to 1. When I'm only going over the outward hemisphere, the integral goes from 0 to 1 instead of minus 1 to 1. We've restricted that range. If I lambda is isotropic, what can I do with I lambda if it's isotropic? Take it out of the integral. It's a constant, so I can pull it out of the integral. Then F lambda will be 2 pi I lambda integral from 0 to 1 of mu d mu. What's the integral from 0 to 1 of mu d mu? Well, you might do it in your head, or you might say, no, I want to see it. What's the indefinite integral of mu? What's the antiderivative of mu? Up to a constant, but if it's a definite integral, it subtracts out. Mu squared over 2, right? It's mu squared over 2. And this time, we're taking its value at 1 and subtracting from it its value at 0. So you get 1 squared over 2 minus 0 squared over 2. Quick, what's 1 squared over 2 minus 0 squared over 2? 1/2, 1/2. And so you just get that that'll cancel that 2, and you get pi I lambda. So for isotropic radiation, F lambda is pi I lambda. Again, it has to be isotropic, but if it's isotropic, F lambda is pi I lambda. Which generalizes our earlier result. That for thermal radiation, and we've already made use of this today. We didn't derive it today, we derived it earlier in the semester. F lambda is pi b lambda, right? Because I lambda is b lambda for thermal radiation. So F lambda is pi B lambda. We found that long ago. And now we see, well, yeah, it's always true for isotropic radiation, whether or not it's thermal radiation or not. As long as it's isotropic, F lambda is pi I lambda in that situation. And we'll make use of this idea later when we talk about what's called the Eddington approximation, for example. But it doesn't even have to have an approximation involved. Note we could also define the inward flux as opposed to the outward flux. And that would just be the integral over the inward hemisphere of I lambda cos theta d omega. So we could just go the other direction. And if there's azimuthal symmetry, we'll have that that's 2 pi times, so now the integral, when I do I lambda mu d mu, what are my limits going to be this time? So if we do the whole shebang, it's 0 to 1, it's -1 to 1. If we do the outward hemisphere, it's 0 to 1. What's it going to be if we do the inward hemisphere? What's the lower limit going to be? What's the upper limit going to be? Not 1, 0, close. What's that? -1 and 0, yeah, -1 and 0. The other half, -1 and 0. You do that, right? Which, if you felt like it, you could say is 2 pi, is -2 pi integral from 0 to -1, if you wanted, I lambda mu d mu. Bottom line is the net outward flux will be F lambda out minus F lambda in. How much is flowing out minus how much is flowing in is the net amount flowing out. Can I erase this stuff, or is anybody still copying this? Anybody still on this board? It's about to die, or at least be erased. No, its memories will be preserved. Well, maybe not forever, not to the end of time, but okay, why not to wear my coat in class? Yes? It says azimuthal. Yeah, that it doesn't depend on phi. Yeah. Because in the above, we multiplied I lambda by 1 power of mu equals cos theta. We say that F sub lambda is the so-called first moment of the radiation field. And if we're going to say that's the first moment of the radiation field, I'll give you one guess as to what would be called the second moment of the radiation field. Instead of integrating I lambda mu d mu, we integrate I lambda what d mu. If it's the second moment, why instead of multiplying by 1 power of mu in the first moment, let's multiply by 2 powers of mu. And if I multiply by 2 powers of mu, why mu is, Cal really wants your attention, or mu squared, just mu squared, right? So we will see, we now show with great joy, we now show joyfully, we always want joy here, joyfully, that the second moment well, that'll be the integral from -1 to 1 of I lambda mu squared d mu is proportional to the radiation pressure. Radiation pressure. Should radiation have pressure? Well, do photons carry energy? Yes, they do. Do photons carry momentum? They do, because remember, in relativity, E squared is equal to what in general? Do you remember in terms of both the mass and the momentum of a particle, E squared was what? So first of all, if the momentum is 0, so that you just have the rest energy, then E equals mc squared, right? I don't know if that's a most famous or second most famous equation in physics, right? Equations people have heard of even if they don't know much physics. The other one, of course, being F equals ma, which is better said A equals F over m to emphasize effects and causes properly. But nevertheless, E equals mc squared if the momentum is 0. So it must be that E squared when the momentum is 0 is mc squared, because I'm using unnatural icky units where c is not 1. And then there's also a piece that comes from the momentum. Anybody remember what it is? It would have to have the same units as mc squared does. What are the units of momentum?
Mass and acceleration.
Not acceleration, that's force. Right? mv, right? Now relativistically it's not mv, it's m gamma v, but gamma is dimensionless. So momentum has mass times velocity units. So what could I use in relativity to multiply the momentum to give me the same units as energy? Because energy has units of what? Kinetic energy has what units? And all energy, therefore. What's kinetic energy? Even in the Newtonian case, we can still use that because the units of energy, even though the expression isn't the same in relativity or Newtonian physics, what's kinetic energy in Newtonian physics? Oh, come on. 1/2 mv squared, right? What are the units of that? Why, that's the same units as mv times v, right? Because mv squared is mv times v, right? So momentum times velocity has energy units. It's not energy, but it has energy units. So what's the only thing that makes sense if I'm going to, in a sense, what would make sense to multiply the momentum by in relativity to get something that has energy units? I need to multiply by a velocity. It's relativity. What's the most natural velocity to multiply the momentum by?
C.
Yeah, C, right? PC has energy units, so the other piece, well, that's not a proof, but it's a plausibility. This is the expression. E squared for a particle is mc squared squared plus pc squared, right? That's the relativistic relation between mass, energy, and momentum. That's just the general formula for a particle in relativity. E squared is mc squared squared plus p squared c squared, which of course you could write m squared c to the fourth plus p squared c squared if you wanted to. In natural units, which I much prefer, it's just e squared equals m squared plus p squared, because in natural units you just make the speed of light be 1. Okay. General. Give me any particle, tell me its mass, tell me its momentum, that's its energy. What's the mass of a photon? It's 0. So what's the energy of a photon in terms of its momentum? What's that? E squared is pc squared, so it's E by itself. PC, yeah. E is PC. Photons are very politically correct, if you like, right? E is PC. E is PC for a photon. Yeah, they carry energy. Yeah, they carry momentum, right? So a photon's momentum, P of a photon, is E of that photon divided by the speed of light. Or in natural units, P and E are equal to one another for a photon. In units where we make the speed of light 1, the units then P and E are just equal to a photon. So there's light shining down upon you. Is it exerting a force on you? Well, sure it is, because every one of those photons has momentum. And if you absorb the photon, you're absorbing its momentum. And if you reflect the photon, you're still getting a momentum transfer, because a photon coming in and a photon going out don't have the same momentum. And so either way, you're transferring momentum. So radiation carries momentum. In a stellar atmosphere, photons carry some of the pressure. And as we alluded to, in a very high mass star, the Eddington limit arises because if there's enough radiation coming out, that radiation pressure can actually be more important than the gas pressure, and for a very massive star can exceed the gravitational force on the outer layers, and so they just get blown off into space by the star's own radiation. But in general, the point is, because photons have momentum, radiation carries momentum. And we can use that to show the claim here, joyfully, that the second moment of the radiation field is related to the radiation pressure. So first of all, pressure. What are the units of pressure? Pressure is force per what? Force per unit area, right? So newtons per square meter are pressure units, right? Force per unit area. And force is rate of change of momentum. So it's also momentum per second per square meter is pressure units. And that's the approach we're going to take here, is we're going to see how much momentum is transferred per second to a surface that has photons bouncing off of it, so to speak, reflecting off of it. So here is a cute little patch dA of an ideal, perfectly reflecting surface. This is a ideal, perfectly reflecting surface, which means it never meant a photon that it couldn't reflect. Every single photon that hits that surface is reflected by it. So let's make a z-axis that's perpendicular to the surface. And let's consider a photon coming in at an angle theta to the surface. It gets reflected. Anybody remember, what's the law of reflection say? How is the angle of reflection related to the angle of incidence? It's a very, very simple, it's completely symmetrical. They're equal to one another. So this is the perfect mirror that I'm talking about here, where it never met a photon, it couldn't reflect, and like every self-respecting mirror, those two angles are equal. The incoming angle, the outgoing angle, they're equal. So I'm going to imagine that there's radiation coming in that direction and reflected back in that direction. And I'm going to get all fancy here and make little solid angle cones, because we are all about loving our solid angle cones, as I'm sure you do by now. So there's a lovely little solid angle cone there. We're going to consider all the photons coming in to that point from within that little solid angle cone. So we got ourselves a d omega here. And every photon reflects symmetrically, so they'll reflect out into a solid angle cone on the other side. And if I drew it perfectly, how should the sizes of those two d omegas be related to one another? Should they be the same or different? The same. They'll be exactly the same. So in other words, every photon coming in from some d omega is reflected into a same size d omega. It's on the other side, but it's the same size d omega. And we're not going to finish this today, but I want to set up this idea. The idea then is, if I have a ball and, okay, it'll move on a parabolic trajectory. Let's be in outer space. So I have a ball, smacks into this, and if we had a perfectly inelastic collision, so it bounced off, if it's a perfectly inelastic collision, then how does the outgoing speed compare to the incoming speed if it's perfectly elastic? Equal, yeah, because the perfectly elastic collision preserves kinetic energy. So how about the momentum? Does the component of the momentum parallel to the table surface change? No, right, because that component stays the same. But how about the component of momentum in the z direction? Inwards, coming in, it's pointing down. Going out is pointing up. So when I take the difference, that's twice the incoming z component of momentum, because it's like z component minus z component is the change in the momentum. And that will be the key here, is that you are going to get twice the change in the z component as being the momentum transferred by any given photon, and it'll be twice the z component of that photon's momentum. Well, the total momentum is its energy over c. How about the z component of the momentum? If it's coming in at angle theta with some momentum p, what's the z component in terms of theta? It's p sub z times what trig function of theta? Cosine theta, right? So in other words, we're going to get 2 times the momentum component, 2 times the total momentum of the photon, times the cosine of theta is how much momentum each photon transfers. And that factor of cosine theta is going to show up as why it's cosine squared theta that gives us the momentum transfer, because the solid angle business, we're going to relate it to the specific intensity, and the specific intensity has dA cosine theta in it, and the z component of the momentum also has cosine theta in it. So there's going to be 2 powers of cosine theta that relate to the rate of transfer of photon momentum to the surface. Because when we come in at steeper angles, the surface is looking smaller and not as many photons get intercepted at steeper angles. And so there will be 2 powers of cosine theta when we figure out the momentum transfer, which means that the pressure is going to have cosine squared theta in it in the end. We'll see the details next time, but that's a teaser. Now you've got something to avidly look forward to next class. Yes. Woohoo! Yes. Tomorrow, yeah, the homework is now due tomorrow because I will be buggable tomorrow.